Hello, everyone. I think I'll get started. So thank you for joining us for our webinar on Infinicyt, a flow cytometry data analysis software program. This software program is made available in the United States through ALPCO Diagnostics in partnership with Cytometry, a company based in Salamanca, Spain. So for those of you who are unfamiliar with ALPCO, just want to give you a little bit of a background about us, and then I'll change the presentation over to Roberto. So ALPCO, American Laboratory Products Company, was founded in 1991 as an importer and distributor of immunoassay-based products for the North American life science markets. Over the past 20 years or so, we've become a premier channel representing over 60 collaborating partners from around the globe. And in late 2007, we launched our organically developed product line, which is focused in the area of diabetes and obesity research. We have also remained true to our roots by continuing to provide immunoassays beyond the ordinary. As we've evolved, we've expanded our offerings to applications for HPLC, LCMS, purified antibodies, recombinant proteins, and most recently, we've added flow cytometry-based reagents, as well as this software program we'll be speaking with you about today. This next year will prove exceptionally productive, as our offering will continue to grow by over 400 new products. So this is really exciting for us, with a specific development focus in our new Stellux line of chemiluminescent-based detection systems. So if anybody has any questions for us during the course of the webinar, if we don't have an opportunity to get to those, my contact information is here. I am the product manager at ALPCO for our immunology product line and specifically the flow cytometry products. And again, my email address is right there. So without further ado, I'd like to introduce Roberto Juanes Juanes. He is a product specialist for Cytometry. They are a biotechnology company based in Salamanca, Spain. Cytometry is dedicated to the design and development of new reagents, software, and techniques that provide innovative solutions in the flow cytometry field. Mr. Juanes was trained in the flow cytometry service at the University of Salamanca. This is headed by Dr. Alberto Orfao and one of the laboratories from the Euroflow Consortium. So I'll let Roberto begin now. And again, if you have questions, please feel free to email.
Okay, so thank you very much, Bethany, for the introduction. My name is Roberto, as Bethany just said. I'm the responsible, I'm product specialist in sector nurse, and I'm the responsible of the webinar today. I will try to explain in this 45 minutes what are the most different features of Infinicyt regarding the flow cytometry software. So I will start with just explaining a little bit where did Infinicyt come from, because well, maybe you have heard about Infinicyt sometimes, but you don't know exactly what is Infinicyt, what's the origin of that. It's from a private company, or maybe you have heard about Euroflow. So I just want to clarify and explain what is the origin of Infinicyt and why it's important for everyone to be here today. We can listen to this webinar. So the origin of Infinicyt is a mixture between industry and academia. The origin came from a collaboration. So as Bethany said, we are based on Salamanca in Spain. In Salamanca, this is one of the most important flow cytometry labs in Europe and the most important in Spain. In this laboratory, Professor Alberto Orfao has had in the past some ideas about how to improve the data analysis of flow cytometry, but he was not able to find these solutions in the commercial and traditional flow cytometry data analysis software. So he patented those ideas and then started a collaboration 10 years ago with Cytometry. Cytometry was at least a private company based also in the same city, in Salamanca, in Spain, that was traditionally developing reagents for flow cytometry. But then, because our field experience with another pieces of software, University of Salamanca contacted with us and we started a collaboration. So we have the right to explore the patent of the University of Salamanca. Then we put it in a commercial software. That is what we are selling, that is Infinicyt software. So we are sure that everything that we put in our software, in Infinicyt, comes from an idea of a person working directly in a hematology lab in the routine basis. So it's nothing that we put there because we think that it's good for the lab. It's something that we know that it's really good for the lab because all the ideas come from a flow cytometry lab. Also, we have a strong collaboration and relationship with the Flow Consortium. A consortium with the idea of standardize the leukemia and lymphoma diagnosis and flow cytometry. So because of this flow cytometry lab in Salamanca is part of the Flow Consortium. Every time that we want to release a tool to the market, we first spread and share this tool with all the labs around Europe, taking part of Euroflow, around 10, 15 labs in Germany, UK, France, Belgium. They test these tools first, and then when we are sure that they are working properly and are easy to use and are understandable for everyone, then we release to the market. So this is the origin of everything I need to show. Tools that come from ideas from the University of Salamanca, and then we put in the software, and before we release to the market, we send to different labs to test everything, to see that it's working properly, easy to use, user-friendly, and then we release to the market. What is the need for Infinicyt? Why am I here explaining Infinicyt today? Well, because of the evolution of flow cytometry from 20 years to now, there have been new technologies, so new detectors, new machines. We have been able to use more lasers, not just one single laser. Now we are working with 3, 4, even 5 lasers in some machines. This comes as a result of using more colors. Okay, so we have a lot of information. This is really nice because we have much more information for each cell, and it's even faster. So we have a lot of information. But what's the problem? All this information becomes that we need to handle more files. To make the analysis of all this information, we require more diagrams, and at the end, the most important of all, the difficult interpretation of the results. We need to make a diagnosis, to give an interpretation of the things that we are analyzing, and with all these colors, all these markers, it's really complicated. So Infinicyt is trying to solve these 3 problems: the handling of more files, more diagrams, and making interpretation of the results. And this is the 3 blocks that we are going to see in the presentation today. So first, we are going to focus on how to handle the problem of having lots of diagrams. Well, in Infinicyt, this is what we are seeing today. We are seeing now in the screen is the classical workspace of Infinicyt. We use as all the flow cytometry software, as the tradition says, the 2D dot plots. So we are using 2D dot plots here when you are displaying one parameter versus another. Okay, this is easy to recognize for everyone, easy to analyze. But what happens when we are using a lot of parameters? Let's say, I'm not talking about 60 color machine, 80 colors. I'm just talking about 8 color machines plus 4 1 3 scatter. We have 10 parameters. So we cannot use all the 2D dot plots because using 2D dot plots, we need to create a lot of dot plots. We have a lot of information repeated. So we need to go one step beyond and then start using what we call the multi-parametric diagram. So in the left side in the screen, we are now seeing the classical diagram that all the software have. We also have this kind of diagram. So 2D dot plot, density plot, histogram, 3D, also statistical plots like box plots. But in the right side, we have the multi-parametric diagrams that are going to help us to analyze all this information. So those multi-parametric diagrams, the most important of them is the APS, because it's the most important we are going to see separately, okay? But I just want to remind that there are other diagrams like what we call comparison diagrams or parameter band diagrams. For example, in the bottom on the right side, we can see the parameter band dot plot, when for each band, we are representing the fluorescent intensity of one parameter. So we can compare easily in just one single diagram for one certain population. In this case, just focus on the green one, for example. We can see for the green population how it is expressing the fluorescent intensity of all the markers at the same time in the diagram. So 8 colors plus 4 1 3 scatter, we are measuring 10 parameters at the same time in one single diagram. So we don't need to create, for example, 10 different histograms or 10 different cubical plots, so we can concentrate all the information in just one single diagram. This is the feature where Infinicyt becomes an expert, okay? I'm going to move to the APS diagram because, as I just told you, is the most important for us. The APS diagram comes because of the difficulty of using cubical plots for the analysis of more than 4-6 parameter files. So when we are using cubical plots, the separation is based in 2 parameters. So we have a high amount of division information, and if we want to use all of them, all the 2 by 2 combinations, the gating becomes slow. And okay, just to follow with the same example, if we are using 8 colors of cytometry, so 8 parameters, 8 markers plus for one single scatter, and we want to display all the 2 by 2 combinations, we need to display 45 diagrams. I'm simplifying here, I'm just displaying 32, but just try to imagine how complicated it is to get in all these diagrams. We want to use all the information. What we traditionally do is, because we cannot spend the whole day gating all the 2 by 2 combinations, we just use some markers for each particular population. So we just use, for example, 3 for an 8 for the cells, 19, 20, kappa lambda for the B cells. But we know that we have much more information, but we are losing this information just to avoid to gating all this. So what we have thought is, why not to put all the information available, so the information about all the markers in the same diagram together to extract and to use all the information at the same time. This is what we call the APS. APS is just automatic population separator. It's a diagram, like you see in the screen, that it's combining all the markers, all the parameters, so all the markers you have, markers plus the scatter, in just one single diagram, and automatically gives you the separation of the main cluster of the sample. How it is working? Well, what it's doing, the APS, is that separating each event from the others, taking into account the expression not only of one parameter versus another, but all the markers at the same time. It's just like creating a multidimensional space where each cluster is placed in one dimension, depending on the expression of all the markers, but then we take a picture in 2 dimensions, and this is what we are representing. So the APS is just a 2-dimensional representation of a multivariate separation. So what we are seeing here is just the APS is giving me 1, 2, 3, 4, 5, maybe 6 different clusters, all the main clusters that I have in my sample. Automatically, we don't need to make any calculations, we just need to create the APS diagram, and automatically it's going to give you all the main clusters that you have in the sample. You will say, okay, if it is multidimensional analysis, multivariate, I don't have any axis, I don't have one parameter versus another. So how can I interpret this? I don't know. Is this cluster in the upper side of the diagram? Is this T cells or whatever? Well, the advantage of the APS is that at any moment we can make a gate and then see in the rest of the plots, or in a parameter band plot. If you remember this diagram, when we are gathering all the information together, we can gate in the APS and then see in the rest of the plot how is expressing the fluorescent intensity of that particular cluster. So, for example, here, using 2 parameters, in order to select the T cells, I need to gate in for one-sided scatter, inside the scatter versus CD45, inside the scatter versus CD3, and inside the scatter versus CD19. I'm using 1, 2, 3, 4, 5 different parameters and 4 different gates to get my T cells. The APS is doing exactly the same. It's taking into account the information of the scatter, 45, CD3, and CD19, and automatically it's separating this cluster. So what I need to do that, gate this cluster in the left side of the APS and see how is the expression in the rest of the plot. So with one single gate and one single diagram, I'm just doing exactly the same job that I'm doing with 4 different diagrams and 4 different. So the APS is working exactly as we do in our head. We just place all the necessary diagrams to select our population and start doing all the gating, selecting exactly what we want to select. The APS is doing that, but not only using these 4 or 5 parameters, using all the information available. So in this case, apart from using 45, 3, 19 indicators, it's using also the rest of the parameters. So 38, in this case, kappa lambda, 4 and 8. So all the clusters, all the parameters that are in the sample, I'm using to select and separate these clusters here. This is another example where we can see how the APS is able to separate clearly all the main clusters, and then we can see in the classical plot how these clusters that the APS is separating are clearly defined in the list. The advantage of the APS is that it does not separate all these clusters automatically, helping us to identify all the main clusters that we have in the sample. But it's also giving me information about which parameters, of all the parameters that we are using, are the most important to get this separation. So, for example, in this example, what I'm doing is taking all the cells that are 38 positive and then place them in an APS. The APS automatically is able to separate one big cluster in red and another small cluster in green. And then I ask to the APS, what are the most important parameters to separate these two clusters? If I have this information, it's telling me the most important are 4 white scatter, 56, and 19. Even with the percentage of significance, so you can see 42, 21, and 13.2% of significance. So those are the most important parameters, the most different between the green cluster and the red cluster. If I want to check if this information is correct, I just can go to the classical 2D dot plot and place a forward scatter versus 19 and 19 versus 56. And using this marker, automatically you can see that the green and the red are completely separated. In the traditional way, I need to create all the 2 by 2 combinations, select the 38 positive, and find in all the 2 by 2 combinations the green and the red. But with the APS, we are doing that automatically. It's analyzing the parameters, seeing what with them are the most different, and then separating them. So this is the advantage of the APS. For example, when we are creating new panels, and we are not sure if to separate 2 populations or 1 patient healthy and 1 with another of certain pathology, we are not sure if the antibodies that we are using are the best ones, are useful to discriminate diseases, to discriminate populations. We can set a panel, make the analysis, and then ask the APS, are these markers that I'm using relevant to get the separation between these 2 populations? And we are going to have this information automatically. So we can see that with the APS, we are avoiding this problem of handling tons of diagrams, all the combinations 2 by 2, all this information that we have now, because it's going to give us all the information we need automatically, all the clusters, and also which markers are the most important to separate those clusters. So we can say that with the APS and other multiparametric diagrams that the most important is automatic population separator, we have solved the problem, the first one, that is the use of more diagrams. Next problem, we are going to see how we can solve it. This Infinicyt is handling more files. What I'm referring with handling more files? Well, I have said at the beginning of the presentation that we now have machines that can measure 16, 18 colors, but it's not the extended. So what we have, what we have traditionally is 6, 8 color machines, but we want to measure a lot of antibodies. For example, we can have panels of 30 antibodies, 32 antibodies. We have no machines to measure so many antibodies, so what we need to do is split our sample in different aliquots and then put a certain amount of antibodies in each aliquot. Traditionally, what we are doing is, okay, I have my first aliquot, I send with certain antibodies, and then I get the report for my first aliquot. Then I do the same for the second, the third, fourth, 5, so many aliquots. I have to split my sample. And at the end, once we acquire each aliquot separately and analyze each aliquot separately, we put all this information together at the end to make a final report. But we think that this is not optimal, because what we are analyzing is not aliquots. We are analyzing a patient, a sample, and a specimen all together. So we want to have all the information together at first to make a global analysis of this sample. With Infinicyt, we can do that. So if we have different aliquots with different information, different antibodies, we are going to put all this information together at first. We are going to merge all this information together in just one single file, and then we are going to analyze all the aliquots together as a whole, as a sample. We are going to analyze our sample instead of analyze one aliquot, one, two, whatever. So doing that, we are going to have all this information together in the same file, and we can make a report with all the information. Just to see an example. We have a sample of bone marrow in this particular case, and we have split it in 5 different aliquots. For each aliquot, we have acquired 100,000 events per year. In all of them, because this is a panel designed for the study of acute leukemia, we have, via acute leukemia, we have some markers that are common in all the views in order to select in all the views my blood cells of B limit. So in all the views, I'm going to have 4-1 scatter, of course, they are always common, 34, 19, and 45. Those markers are common to the 5 different views, but then I have another marker completely different between the view number 1, 2, 3, 4, and 5. What we are going to do is to merge these files of the 5 aliquots together to create one unique file with the sum of all the events. So if I have 5 aliquots with 100,000 events, now what I'm creating is one unique file with 500,000 events and the information of all the parameters. When I open this unique file, this merge file, what I'm opening is all the individual files, the 5 single files, overlap one on top of the other. So thanks to the common markers, what I can do is to select my blood cells only once. Why? Well, if I'm overlapping, like in the picture, the 5 different files, if the expression of common markers is the same to the different aliquots, it should be the same, you know, because the markers, the antibodies are the same, the sample is the same, just as in aliquot. The cytometry is the same, so all the conditions are repeated, so the expression of these common markers is going to be the same to the different 5 files, so the picture is going to be completely overlapped. So I can gauge in this overlap picture, I'm engaging in all the files at the same time. So selecting my blood cells only once, I'm able to select the blood cells in all the files at the same time. Then I can create what we have seen previously, the parameter band plot, and display the whole immunophenotype, the expression of all the markers in my panel together in one single diagram. What I'm creating is the immunophenotype profile of my sample, just getting all one in all the files at the same time. This diagram is exactly the same if I open the first one using 19, 34, and 45 to gain my blood cells and see the expression of the 5 first markers. Then I open the second aliquot, I select the T cells exactly with the same gauge, with the same markers, and see the expression of the rest of the markers, the same with the 3, 4, and 5. What I'm seeing here is two exactly the same, but everything together at the same time. But the file merge, I've seen that it's really useful to have the panels. We have some common markers, but can be used in a completely different way. In the previous approach, what I'm doing is to merge samples of the same aliquots of the same sample, same patient, to make a global analysis. You have to have a final result all together in the same file. But what I can do with the file merge is merge samples completely different patients, and then make the interpretation of the results and comparison easily in the same window, in the same diagram. To explain that, I'm going to use this example. When I have 4 different samples of tonsil, I have 7 different samples of peripheral blood, and 7 different samples of bone marrow. So all the patients, all the samples are completely different from different specimens. But I want to study how is the expression of certain markers, in this case 38 and 138, on the plasma cells of the tonsil, peripheral blood, and bone marrow. So what I'm doing is I have analyzed each file individually, traditionally, so one by one. But then once I finish with my analysis of the plasma cells on each sample individually, I merge all together with Infinicyt, and I can display one diagram like this when I'm comparing each column is the plasma cells of each patient, and I compare how is the expression of stereotype. I can do the same, but using 2 data plots. So you can see that gene expression of 38 and 138 is completely different between the plasma cells of Tonsil, peripheral blood, and bone marrow. I'm able to display everything together in the same diagram because I'm merging all this information with Infinicyt. Or we can see in a parameter band histogram like this. So traditional, how is the fluorescent intensity for each marker of my panel, depending if I'm analyzing plasma cells of peripheral blood or plasma cells from bone marrow. So you see that with the fine merge, we can have 2 different approaches. We can use it to make global analysis. That means that I'm merging different aliquots from the same sample to make a global analysis thanks to some common markers that I have in my sample. Or I can do a completely different way. I can analyze each file from different patients, different samples individually, and then if I want to compare easily in the same diagram and to make a report of this comparison, I can merge all these analyzed files together in Infinicyt and display quickly all the comparisons of the different samples. So thanks to this tool, to the fine merge, we have solved the handling of more files, of tons of files that we now have now because of the technique. So we have seen the 2 first blocks, how to solve more diagrams, multivariate analysis, how to solve more files with the fine merge, or how to use file merge for a completely different purpose, like the comparison. But we now have to face the most important and the most difficult part of the flow cytometry, that is interpreting the results. We can use the APS easily to separate all the clusters. Okay, that's nice. We can also use the fine merge to make a global analysis or to make comparisons. Okay, that's also nice. But we need at the end to make an interpretation of those results. When I'm analyzing and I'm separating, it's normal, it's pathological, so what I'm seeing here. So for the interpretation of the results, we are going to see different tools, 3 different tools, depending on which kind of studies we are doing. The first one we are going to see is called reference image. Okay, this red population that I'm displaying here is a case study. We don't know what it is. We have just run a panel. We have selected all B cells because I have a suspicion of some B cell pathology. But now with all these markers that I'm analyzing for this sample, I need to discriminate it. What I'm seeing here is normal, pathological, or what. To make this simpler, instead of displaying dot plots, I'm going to simplify this picture, and I'm going to show exactly the same information, I mean the expression of all the markers in my panel, but summarized in this parameter band histogram. So I have in red my case study. I can see how the expression of all the markers, but now I need to make the interpretation. This pattern, this immunophenotype profile that I'm seeing here, is normal? It's not normal? What is it? We don't know. So additionally, what we can do is, okay, let's try to remember and put in our head all this information. How is the expression of all the markers I know for all the different diseases I'm traditionally studying, and having a table like this in our head. Okay, it can be done, but it's not the best solution. It's not the most optimal for this. So we need to try to remember we can just trying to compare not with all the experience we have, but with them to compare just with the last case we see a week ago or whatever. So it's not the most optimal. We can also consult in the bibliography, in some papers, in some books that we have, how are the patterns, and if my pattern that we've seen in my case study fits with one particular disease or not. Or I can consult through the internet, in some publication, also online, all this information. But then we thought, if we are analyzing tons of cases every day, we have normal, pathological, we have references of all the pathologies that we are studying, why not to put all this information that we are analyzing every day, why not to save it within Infinicyt, and then when we are analyzing a new case with Infinicyt, use all these references that we have saved to make the comparison, and that's what we call the reference. So if I have this case study, instead of consult out of Infinicyt, what I'm going to do is to call a reference, another case that I have saved previously in Infinicyt, and make the comparison directly in the same diagram. So this is what we call the reference image. I have saved because last week, last month, last year, I have a normal case, a normal patient. So after analyze this normal case and diagnose normal, I save in Infinicyt, and then when I have a new case and I cannot remember if it fits with normal or not, I'm just calling my reference image. I'm painting my reference image as a background image, as you can see in blue, and now I can do the comparison. What I can see is, for example, the expression of CD3 or CD19 fits with the normal. My red one has in the same position that the blue one, but another markers like CD20 or CD38 or 79B are completely different of the one. So I don't need to remember where is my blue reference because I have it stored in Infinicyt and I can call at any moment and use it to make comparison. Just trying to think how we combine this reference image tool with something that we have seen previously, the finders. What we can do is to, instead of using our reference based only one particular case, we can merge 150 normal cases that we have analyzed in different years and create a normal reference, a strong normal reference, not based on only one patient, but 15, 50, 100, 200. So when we are going to use this reference to compare, we are going to be sure that we are covering all the variability between different patients. We can do also here, I'm using a normal reference, but we can create several references, not only normal, we can create reference for diseases, and then if it's not fitting with the normal, we can load a different reference from one disease, and then see if my new case fits with a particular disease or not. Because it could be tedious or more complicated to create all these references, we are going to see later, in a couple of minutes, how to simplify this with another tool, the Compass one. But this is the origin of the tool that we are going to see later, and it continues to be useful to make comparisons directly in our diagrams instead of trying to remember the patterns or consult the patterns in different places. For example, to finish with reference image could be useful to diagnose with MRD because I can store not only reference of normality, I can create different reference images for a particular patient, like in this case, when I'm saving as a reference the pathological population of my patient at the diagnosis time. So when I'm doing the follow-up after the medication, I can at any moment call my reference image to compare how are my results now with the results at the moment of the diagnosis and see if my patient is getting better or has a relapse or whatever. Because at any moment I have the information directly in the same diagram with my patient, thanks to the reference image. So you can create different reference images instead of for all the population, just for one particular patient and make the follow-up. But now I'm going to talk about the Compass tool that is like an evolution of what we have seen now. Now instead of compare my case against one reference at a time, what I'm going to do is to create a database of different groups of reference, and then when I have a new case that I don't know what it is, I'm going to tell Infinicyt, please compare my new case, my case study that I don't know what it is, against all the different groups of reference that are composed of of different cases. Okay. I want to remark that this Compass tool is an async diagnosis, is not a diagnostic tool, it's just a tool that is going to help us to define if my new case fits with the expression of or has a immunophenotype that is similar to one group of reference. Just to see how it works internally, I'm going to explain this. But before continue, I want to remark that this Compass tool can be used only with certain requirements. So if the operational protocols are standardized, we have same antibody panel, same sample preparation protocol, same cytometry setting, and we are comparing the same population. The Compass tool works comparing one pathological population against the same population in different diseases, not the whole sample. Okay? Compass tool is combining three different things that we have seen today. The powerful of the APS to separate different clusters regarding the spreading of all the markers, data integration tools like the file merge, and the concept of reference limits, so putting a reference in the background to make the comparison. So combination all these tools, the three different tools, we have created the Compass one. To see how it works, we are going to see this example. I have this case from the group number 1. You can see the expression of all the markers for my pathological population, that is the B cells in this particular case. So the rest population are my B cells from a patient, and after gauging my B cells, I don't know if this fits with normal, with CLL, with high leukemia, follicular lymphoma, whatever. I don't know what this is in my case. But what I'm going to do is to simplify. Instead of seeing all the dot plots, I'm going to simplify in the APS. So now my APS, because it's a clonal population, a pathological population, is not able to differentiate between any subclasses, so it's just painting my population as a whole in the APS. To simplify more things, what I'm doing is merging all the reference cases, so group number 1, the red one, and because all of them belongs to the same group, to the group number 1, with my reference, the APS is able to put all of them overlap in the same position. So remember, the APS is using information of all the markers to differentiate cluster regarding the expression of all the parameters. Because all the cases are from the same group, so have the same immunophenotype, all of them belong to the same pathology, the same disease, the APS puts all together in the same position. To simplify, what I'm doing is instead of displaying all the dots, I'm just representing each case, each patient with the median value of fluorescence. And to have more confidence, I have 2 standard deviations. What happened now is I have another cases, but from the reference group 2. So those new cases, the green one, have a completely different disease, it belongs to a completely different pathology than the red one, with a completely different immunophenotype. So the APS, regarding the expression of all the markers, is able to distinguish between and discriminate perfectly all the cases of the group number 2 and all the cases of the group number 1. Just to repeat, is separating group number 1 and 2 in the APS, all the cases, because the expression of all the markers at the same time. What happens when I have a case study, the blue, and I don't know what it is? I can use this APS as a reference image and then plot my new case study and see in which part of the APS, regarding the expression of all the markers, it's placed my case study. So if my case study, like in this case, is placed exactly in the same position that all the green cases, it's because the immunophenotype of this case study is similar to all the cases in the group number 2. So I can say, okay, my new case study, I don't know what it is, has a similar immunophenotype than the green one. So it's not red, it's not that disease, but it fits with the green. So it's going to fit probably. We are not going to be completely sure because you are there analyzing, you are there expertise, but we can be for sure that the immunophenotype, at least by process geometry, the immunophenotype is similar to all the cases that I have said as group number 2. So I don't need to create all the reference images and load all the different reference images because I have all this information here in the APS. In this case, I'm using only 2 groups of reference, 1 and 2, but I can have more than that. So for example, in this case, I have 4 different groups of reference, 2 blue, 1 red, 1 green, and I'm comparing my purple case against all of them. In order to simplify and not to display all the 2 by 2 comparatives and see and analyze in all of them where is my case, because we go back to the problem with the diagram, we need to simplify that. We are displaying this compass diagram, this needle, that is pointing me directly to the group that is more similar in terms of immunophenotype to my case study. So we just need to create a database of reference, different groups of reference. So this is number 1, 2, 3, 4, 5, normal with different cases in each group, and then tell the software, just compare my new case against all the reference groups that we have in the database. Regarding immunophenotype, it's going to see the expression of all the markers, and it's going to guide you to the results. It's going to tell you, okay, the case study is more similar in terms of immunophenotype to the group number 1, 2, 3, 4. So it's helping you to make a decision on what to do this case study. Of course, the result is not always 100% sure. If the case fits in all the comparatives 2 by 2 and in the single comparative, it's going to have a complete pointer. If it's in all the 2 by 2 comparatives but not in the single one, it's going to be partial pointer, or it can be a null pointer if the immunophenotype is not similar to any of the immunophenotypes that we have saved in the data. Okay, so take the results of the contact tool carefully. And just to finish with the interpretation tool and with the third block of the presentation, another tool based also in the concept of reference image, but not for the study of clonal populations like the contact tool, but for the study of bone marrow. What are the difficulties? Well, here what we are seeing is not just clonal population with a particular immunophenotype. In bone marrow, what we want to see is the evolution, the maturation from the more immature stages, from blood cells, to the more mature. You can see in this picture how for the neutrophils, for example, I can have different patterns of maturation depending on the marker. The most classical is the 11-13, from the preneurocytes to the more mature neutrophils, right? But we cannot learn all the patterns for all the 2 by 2 combinations in all our patterns, for all the populations, neutrophils, monocytes, leukocytes. So we are going to do exactly the same that we have done, but instead of saving just clonal populations, we are going to save the whole pattern of maturation. So to study pattern of maturation with Infinicyt, we just need 2 steps. So identify the study population, in this case neutrophils. We see in the 11-13 how from the more immature follows this pattern to the more mature, and then because we know that this is the path from the more immature to the more mature, the second step is draw this maturation path. So I just need to select in Infinicyt, draw the maturation path, and draw a line from the more immature to the more mature. Automatically the software splits this population in 20 by default different stages and takes the median value of each stage of the element B13, giving me this diagram as a result. So from the more immature, when I start to paint the maturation to the more mature, the end of my line, it takes the median value of fluorescence and then represents the line. So we can see that from the more immature and the more mature, how evolved the 13 and how mature the 11 is. Okay, this is perfect with 2 markers, but we want to do exactly the same for all the markers. So what's the diagram in Infinicyt that use all the information, all the markers at the same time? Right, the APS. So if I draw the maturation path over the APS, I'm going to have the same diagram but with information of all the markers, not only elements. So yeah, identifying my population and drawing a line from the beginning to the end of the maturation, I'm able to see how is the evolution of all the markers from the more immature stages to the more mature in one single diagram. Now I can move to the next step to make the interpretation. So what I can do now is do the same for example, 3 different normals. So merge 3 different normals and draw the maturation and save that as a reference image. But in order not to have a mess of lines, we are just going to normalize in a single line my normal cases, my normal reference. When I have a new case that I don't know what it is, what I can do is apply the same maturation path that I have done in normal reference over this new case and compare the expression of all the markers against my reference. My database of reference is this line that I have normalized. So everything that fits with the gray band is normalized, and everything that is over and or under my gray line is underexpressed or overexpressed. So now I can make the interpretation of the results. When I have a bone marrow that I don't know if the maturation fits with the normal or not, I just need to compare against all my reference databases of normality that I have created and see in which stages of maturation and which parameters are under stress and over stress. So you see, when this we find and the block of the difficult interpretation, you have seen that we have just put in for the interpretation of the results all the information that we already have, but we put it in the computer within Infinicyt. So at any moment that we want to use it, we just need to click a button and automatically load all this information. It's the same that we are doing every day to make interpretation of the results, but now do it by the computer, right? So finishing with this, with interpretation of the results, I have covered the 3 topics I want to speak today. The 3 things that make Infinicyt completely different from the other software, and the things that we think that help you in the daily routine, in your routine analysis of the flow cytometry data. As I told you, those are things that we have put in the software because people demand it, people keep using it, people here, not only in Salamanca, but around Europe and the rest of the world are using these tools in the daily routine, in the daily basis. So I just wanted to present it today. I hope you enjoy the presentation. Of course, thank you very much for attending this webinar. Of course, thank you ALPCO for organizing. So I'm just going to pass the word to Bethany if she wants to say goodbye to everyone. So once again, thank you very much, and I hope see you in the future.
All right, thank you, everybody. We do have 3 quick questions that we'd like to address, and then we'll let you go. So we had one person ask how many parameters can be analyzed in one APS. Roberto, would you mind answering that, please?
Yeah, it's no problem. There is no limit. We have tested with 200 parameters, it's the big file that we have, but theoretically there is no limit in the APS, so you can use as many parameters as you have.
The next question is, can you repeat colors in all of the tubes when you are doing file merge?
Yes, exactly. You can repeat colors. You can have some common markers with the same color that are repeaters to different tubes, so this is not a problem. You can merge whatever you want, depending on what you are merging. You are going to use a global analysis or to make comparisons, but of course you can repeat markers. There is no limit in that sense.
Okay, and the last question is, when you are doing file merge and you have those common backbone markers and for some reason they don't overlay, will the software program give a flag that there's inconsistency?
Yes. Yeah, exactly. We have different controls in Infinicyt that you can customize that depending on the threshold that you select, the percentage of difference between these common markers is going to flag and warn you which markers are more different and in which files of all that you are merging is the difference. So there is controls that are easy to consult and are going to help you, yes, of course.
Okay, well, thank you everyone for joining us today. If you would like a recorded version of this webinar, feel free to reach out to me. You can either use the email address I provided at the beginning or respond to the registration email that you received. Thank you.